Yeah, yeah, it's
Is it
visible.
visible?
Yeah, content. Yeah.
Yeah, sir. Okay, sir. So physical design will be is a we'll start with physical design where it comes and we will SI. So after that, this one synthesis team they will given some input files. So then we will start our backend design. So that will be the physical design. So first we'll go with the introduction of physical design. Okay. So what is physical design? So okay, one second. Someone are coming. So still some more are there, sir, or the-
Yeah, they
still the
will keep
students
on
are
join.
joining.
Yeah, they will keep on join. Yeah.
Okay, okay. Sure. Yeah. So physical design is nothing but what it is converting that netlist into a GDS form. So here the netlist will be given by synthesis team. They will give some input files. So using that files, we will importing the designs. Okay. So that is nothing but what physical design, and also we call as it is a process of converting converting the netlist into a GDS form or logical connectivity of cells converted into a physical connectivity. This is called as what physical design. During this physical design, what actually will happen means all the design components are instantiated with the geometric representations. In other words, we call that names as macros, cells, gates, transistors, and all. So before that, what happened in the synthesis team that all the data will be presented in the what code form, either it is in a VHDL or Verilog or system Verilog. So it will be in a code format. Okay. So later, what it happened, it will instantiated with some geometric representations. So that we call as macros, cells, gates, transistors, and etc. We'll show you that what are the macros and cells, transistors, and all. Show it in that project. Okay, one second. Yeah. So and that all the structures will getting some shape and sizes here. The fixed shape and sizes per fabrication layer are assigned to the spatial location and have appropriate routing connections in the completed metal layers. Okay. So physical design is directly impacts on most probably performance, area reliability, power, and manufacturing yield. So these are the main parameters the physical design will impact. And first one, if you see go with the performance, if the long routes have significantly longer signal delay. So obviously in the chip or in our block, if we have a longest nets means, then obviously the delay will be more, right? Due to that delay, longer signals will be goes very slow. That is the main. It will impact on the performance of the chip. Second one, area placing the connected modules far apart result in the larger and slower chips. Suppose the cells are more means if you placing that cells so far means then what happen obviously the data transfer from one cell to another cells it will be very slow. Due to that again the chip functionality will be slow, so area also will matters more. And reliability, one second someone or coming, I will admit all. So yeah, reliability. A large number of wires can significantly reduce the reliability of the circuit. So this is the main thing. And power, coming to the power, large transistors and longer wires results in the greater dynamic power dissipation. So if the suppose the transistors are more means obviously switching will be high more, right? So due to that switching, what happened? Dynamic power consumption will be more. So if the dynamic power dissipation is more means, then the even the reliability also impact. Yeah. How many are there? So yeah, coming to the PD flow. So this is the flow. So we need to follow for physical design. First will be the first step is input files. These input files we will get it from the one is synthesis team and another is some vendors and foundry also we get it some input files. Using these input files only we need to start the physical design. So this is the first step input files. We'll go what are the input files, what it contain and all one by one step by step. But the first step is input files. It is nothing but a what the GDS files. The GDS files will be the first step is input files. given are proper or not. That we call as what? Sanity checks. Okay. So sanity checks and then floor plan. So suppose the input files are proper, there is no error in that, then we will start doing the first step in physical design, that is nothing but a what? Floor placement, boundary creation, core boundary creation, and physical cell placements. These are the some physical shelf placement, macros placement. So these are the some steps which followed in the floor plan. Then next coming to the second one is after floor plan is power plan. So power plan is nothing but what? Distributing the power to the each and every cells of the design. So that is the power plan. There, so during this time, all the stripes will be created, rails will be created, and rings will be created, and even some causes we getting like electron migration and IR drop, voltage drop. So these are some causes we get it during the power plant. We need to sort out it, and we need to distribute the power to the each and every cells of our design. So that is the main targets of our power plant. Coming to placement, so this is a placement is a very big what we call. So here the tool will start placing the all every standard cells. Okay. So tool will start what? It will start placing the standard cells in the optimized core area, and here we get congestion issues and all. So we need to sort out that, and we will need to take care of that. One second, yeah. Then after placement, so placement optimization. So the placement optimization, nothing but what? Area will do some optimization for the better routing area, routing stage. So it will start doing some if any forest nets will be there, so they will try to connect it nearest to that, or else some if any delay will be happen in the signals, then again that tool only automatically add some buffers to that signal for the strengthening the data, sending the signal from transferring 1.1 to another part. So for that, they will adding some buffers to that So for that, they will adding some buffers to that. Then after that, we already know for that like for sequentials, we need some clock, right? If any soft signal, we need to distribute for that. So that is nothing but our CTS, clock tree synthesis. We call. So CTS is nothing but a what? Distribution of clock port. So this is nothing but a what? CTS. CTS optimization is nothing but a what? Same. So what happened in the physical this one placement is same. Here also tool will start doing some optimization for the better routing routing stages. So that will be take care in the CTS optimization. So they will adding some techniques. They will follow some rules. So that will be done in this one CTS optimization stage. Coming to the routing stage, so this is the last stage. Here what happened, the all the logical connected cells will be connected with the physical nets here. So this is the last step of a physical design. So here each and every cells will be connected with the physical nets. So physical nets, and all the timing consent should be met, and all the uh, area, everything, time, area, DRC, DRV evaluations, everything will be taken here, and that routing will be done at the of last stage, routing optimization stage during that time. So coming to the first step, as I told, this is the input files which we need for the physical design. I will wait. I will allow some students. So yeah. So these are the input files for the physical designers. So first one is what? Netlist file we call as netlist. So netlist is a in the extension of .v. This file will be given by the synthesis team. Okay. And coming to synopsis, design constraint, synopsis design constraint. So this is the file. So it will be in the extension of .sdc, and which containing the data in a TCL scripting type. And this is also given by the what? Synthesis team only. And these are the two files which you get it from the synthesis team. And these are the input for the physical design. Next one will be the timing library. So timing library will be divided into one is timing and one is physical library. So this is .lib we call this is timing library, and .left we call a physical library. And these two files we get it from the vendors. Hope you get it right. So .v file and .sdc file, these two file get it from the synthesis team, and .lib with the .left, and these two files get it from the vendors, and technology file and table lookup file. So these are the two files we get it from the Foundry team, and the extension of these two files are techlef and table lookup. We call as table lookup file or else .tlup. So these are the inputs we need for the physical design. Yeah, so now we'll see one by one what that files will contain. First file is what? Netlist file. This is given by the what? Which team? Anybody? Which team?
Synthesis team.
Yeah, good. So this is given by the synthesis team. What actually it contain? So textual description of circuit components, like logical gates, combinational circuits, sequential circuits. So netlist is totally collection of gates, and it containing the logical connectivity of all the cells, and it can be a collection of registers, capacitors, or transistors. An example for the netlist. Suppose AND gate is there. Okay, so AND gate data will be present in the netlist file. How it will be in that file? So we need to see that, right? For that I added one example here. So this is in the format the data will be present in the netlist file. Module and gate y comma a comma b. So this is a y is output, a or b are the this one code in this one, right? What we call design verification time. You will wrote some codes and you will do some simulations and all. So same thing only will be present in the netlist file also. It is in the Verilog code we call, or a system Verilog we call list as. So it will be start with the end module and end with the end module, and in between that all the data in that gate input and outputs and what the functionality it will be do. So all the data will be present in that file. Same like that, each and every cell's information will be present in what? Netlist file. So apart from this, even this netlist file containing some extra informations like hierarchical information, module informations, instances informations. So these are the some data will be present in netlist file. But the main thing is what actually it was contained is this type of data. Got it? Yeah. Second one, so synopsis design consent file we call it as. So this is the file which contain there are timing constants used to make the timings. So suppose they will this was given by the what synthesis team only, and here it will contain some timing constant information to meet the timing our timing what we call mm, violations will be reduced, and it will be met our timing values. So that will be the main thing. And what it contain actually, first one is create clock definition, generate clock definition values, virtual clock values, input delay, output delay, max delay, min delay of our block, max transition, max capacitance, max fan out, and some path exceptions we call it, these all like multi-cycle path, false path, half cycle path. So these are the input which are present in this one synopsis design consent file. So this is the data. Okay. And yeah, coming to the library, timing library file, as I told, library will be divided into two types. One is logical library, and one is physical library. So first one is timing library. It is containing some logical libraries like I'll just concentrate on this one, what the data will be this file contains. And it contains some functionality in form of standard cell side, soft macros, even hard macros also. Yeah. One second. Sorry guys, just one call. Yeah. So where is timing library, right? Still the people are joining. That's okay. Okay. Yeah, timing library which containing the timing information of the standard cells, soft macros and hard macros, and it contains the functionality information of the standard cells and soft macros and even hard macros also. And timing informations like a cell delays, requiry time. So these are different different timing data will be present, and some which will containing some power information also. So power is nothing but like two different powers, like switching powers, switching power, and again in switching internal power, short circuit powers. So these are some different different power informations also present in timing library. And cell delays depends of the depends of the input run and output load, and it is calculated based on the table of tables. And physical library, so what it contain actually, so it containing the physical information of the standard cells. What the timing library contain only standard cells, soft macros and hard macro, but the physical library containing only physical information of the standard cells, macros, pads. What is the physical information is nothing but what the standard cell height, width, how much area it will take for the placing and location. So these are the data which will be present in physical library. Okay. And containing the name of the pin, pin location, pin layers, direction of in, either it is a in or out or in out, and use of pin, either for which purpose we are using, for signal or power or ground purpose, and some site row information, height information, and width of the pin information, and cell. So these are the data will be present in physical lab, and which will containing the height of the standard cell placement rows. So rows is nothing but a site rows we call it as. So this is the actual height of the standard cells, actual height of the standard cells. And macro information like a cell name, size, dimensions, yeah, and layout, blockages, and capacitance. These are the will be defined in the physical library only. And design rules, via definitions, metal layers, and metal capacitance also will be present in physical library. Okay. And coming to TechLab file, coming to TechLab, yeah. So containing the number of metal layers and how many metal layers which we are using for in our project or in our block, and vias, and each and every via names, which will be present in what technology file, or we call as TechLab. We call as what TechLab also, technology file. And design rules for the metal layers, like the width of the metal and spacing between the two metal layer resistance and capacitance, as well as routing grid. Maximum current density is also present in the tech file, and the physical and electrical characteristics of each layer and via. So these are the data which will present in tech left. Even it containing the some annual and PL metal pitch. Pitch is nothing but what the distance between the two same metal layers we call as what pitch. So this pitch data information will present in technology file. Coming to the table lookup file, so this is a updating file we call it as. So suppose if we do power plant, so some of the metal layers will be we are already placed in the area. So for each and every metal layers, that length will be calculated with the RC values. So that RC value data will be present in what table lookup file. So it is a table containing the RC values at a different net lengths and spacing, and contains a RC coefficient for the specific technology. It will be depends upon the technology which tool we are using, and these RC parasitics are used for the calculating the net delays. So for the calculation of delay, we are using these RC values. Yeah, up to here, the input files information we will completed. So now we'll start go with the sanity checks, whether the given input is correct or not. That we call as what sanity checks. So every library team and synthesis team is correct or not. Data stage of our design. So that is the purpose. Before start doing our physical design, we need to check whether the given input is proper or not. So for that, we need to do the sanitization checks. Basically, we are checking following input files, make sure that these files are complete and not honest. So that file one is netlist file and one is SDC file. And for SDC and library, we'll do only with a single command. So because both having some same timing information, some input delay, output delay, and some all the data will be same only. That is the purpose. For these two, we'll do only in a single command. But for the netlist, we'll give separately. So first we'll go with the what the tool actually will do. If we give some command to the netlist file, so check that file netlist file is correct or not. So if we given that one, then tool will start doing this. These are all the parameters the tool will follow. One is check if the current design is consistent or not. It checks the quality of the netlist and identifies the first one is empty modules, floating pins, multi-driven nets, undriven input ports, unloaded outputs, pin mismatches count between the instances and its references, and tri-state buffers. So first thing is what empty modules are there or not. As I told, netlist file containing what this type of information, right? Like a module and date and input a comma b output y and end module. So this type of data will be present. Suppose we are the humans, right? So we did some mistakes during the writing the code. So that time, if we wrote two modules and modules empty modules, so that modules will again will which creates the what we call extra empty cells during the physical design. So import while doing importing design, so unnecessarily it one extra cell, so that that will be effect to our chip only, right? Because that again that cell need one locations and some area, again they need some power, we ground everything, again we need to give the everything. But for the there is no logical and physical connectivity of that cell because it is a empty cell. So for that purpose, any empty modules are there or not, we need to check. So we not checking, the tool will do this one. By default, tool will start checking the empty modules are there or not in the netlist file. Suppose if any empty modules are there means automatically it will show in the console. So empty modules are present. So we not modify any input files. So if any errors we got like any empty modules, porting pin, driven nets, undriven nets, we need to report it to the synthesis team itself only. They will take care of it, and they will again sort out that issue and they will send it back to the PD teams. So we can't modify anything here. And second thing is what floating pin. Floating pins will be mainly at input side we need to check. Why? Because suppose if you take example CMOS inverter and the two gate terminals of these PMOS and NMOS will be connected to they will shorted and connected to a single input, right? So if any and even that CMOS having some noise margin. Suppose if that input is not connected to anything means unnecessarily some noise will be enters into that. So that noise will disturb the functionality of our the CMOS. Suppose that input that coming noise will be lesser than the noise margin of CMOS means then it won't affect to the functionality. So if it is more than that means obviously it will be affect to the whole functionality of the transistor. And that CMOS transistors output will be connected to the another transistor, right? So suppose one transistor will be affected means whole that overall that whatever that output will be connected, another cells will be connected to that output, that all the cells will be again getting some issues. So that is the purpose we need to check the floating pin at input side, main thing. And any multi-driven nets. So single net will be driven by the two different nets. So that we call as what multi-driven nets. So if anything is there, means again it will be affect to the timings. So that should be checked with the netlist time. Netlist checks time, checks timing that time. And coming to unloaded outputs. So unloaded outputs at the output side for any output load is more means obviously the transferring the data from one point to another point it will be takes more delay because of the less transistors and all, sorry, less buffers. Using a full adder for the thousands of time in our project. So 1,000 full adders are there, but we can't possible to give the same naming full adder, full adder, full adder. We need to give the name with the full adder one, full adder two, full adder three, like that only, right? So if we give the full adder one, full adder two, then If you give the input A1 B1, for another one will be the A2 B2 A3 B3, like that if you give, then obviously the tool will takes the proper inputs when we giving when it will calling the in outputs. So if the pin will be mismatches, suppose if you give the by default, if you sometimes you give the full adder one same names, then tool will take the same inputs from the two cells also, like a A1 A1 A2 B2, like that. So this will be happen for the it will affect to the again functionality. So that is the purpose we need to check any mismatches will be happen in the instances or not, and any tri-state buffers are there or not we need to check. So tri-state buffers is nothing but a what, always on or always off cells we call it as. So always on and always off. Suppose in the design we need in the either it is in a series or in it is horizontal or vertical, whole one line cells will be we need to on. So this is our uh, target. So for that, if we add one tri-state buffer at one first cell only, automatically that whole line will be always on. So that's how the tri-state buffers will be works. So these type of tri-state buffers will be uh, placed in our even in our phones also, they will be used most tri-state buffers. So where we can get it means, like suppose if you switch off your phone today and you can switch it on around after 1 month, even the battery is also dead, and you can remove the battery also, and you can switch it on later 1 month, but the timing will be shown will be same only the time. Why? Because the 555 IC timer is there na, in each and every mobiles. That timer IC we getting a power from this type of tri-state buffers only. So these are the always on cells. Even there is a no power source, power supply also, these tri-state buffers will be always on. They will getting the power from the secondary substations, or we call they will getting power from the some outside source also. Suppose due to that more temperatures, or sometimes we can hold the phone more heat with the hand, means some heat will be generated, so due to that heat also it will be take the power. So this is the functionality of the tri-state buffers. Hope you got it right. Yeah. So second will be the SDC file. So here in this SDC file, that as I told, some path exceptions will be there. So these exception paths will be defined properly or not in this file. So that will check during the sanity checks for the SDC file. First one is multi-cycle path. Second one is false path, half cycle path. Multi-cycle path is nothing but a what? The clock will take more than one cycle to generate the output. Is called as what? Multi-cycle path. Okay. So clock is takes more than one clock cycle for generating the output. That is called as multi-cycle path. So if any this type of paths are there means, it should be present in the it should be defined in the SDC file. Either it was what with other, it won't consider the multi-cycle path. And false path. False path is nothing but what? It won't have any logical or timing information, timing data. So it won't consider for the timing constant. So that type of paths we call as false path. Suppose in our project 100 paths are there and one path is false path. uh, if that false path is not defined properly in the SDC file, then the tool will start doing what? It will start doing timing that iteration for the 100 path also. So that is the purpose we need to mention that one. So this is a false path. Don't consider for the timing. So that should be mentioned properly in the SDC file. So that will tool will check here. Half cycle path. So half cycle is nothing but our path cycle will be 50%. So if any 50% paths, paths will be there means, that should be defined in the sanity so there are meeting we need to check whether the clock is reaching to all the clock of the flip flops or not. So it won't matter because clock will be ideal only, right? So that is the purpose. So we have to check only just if the clock is reaching to clock of the flip flop, check that one. And check multiple having the same registers. So that will also check, and port missing. One second. Yeah. So yeah, we completed the sanitary checks and input files and what that files contain that input files, and we completed the sanity checks. Why we need to do sanity checks? What happen if we not do that? One second, due to some network issue. Yeah. So up to here, no doubts, right? Any doubts? Please, you can ask it now only. Now is it visible? Voice is clear, right? Is it okay now?
Yeah, yeah, continue. Okay, it's okay.
So shall we move on next? So yeah. So next will be the floor plan. So this is the first step in physical design. So floor plan is an art of physical design, and a well and perfect floor plan leads to an ISIC design with the higher performance and optimum area. Floor plan can be challenging in that it allows four steps. First one is what? Creation of, one second, someone asked the question that tri-state buffer is nothing but just like a tri-state buffer is three possible outputs according to my knowledge. One is nothing but what high and low one continuous row means that time we only be using tri-state buffers. Other time we can use normal buffers only. So someone Chinna Babu, yeah, good. So that is correct only what you told now. So that is correct. There are three possible outputs. Yeah. Okay. 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 I can slow. I can go slow. Okay. Okay. Yeah. So yeah, floor plan. So floor plan, as I told, we have some four steps here. One is creation of IO boundary creation. Then second one is what? Port placements. Third one is macro placement. Fourth one is physical cell placement. So first we need to create the IO boundary, or else we call as core die boundary creation. So this is the main area we need to work on that. So this is the optimum area. So this is the first step. And second one, IO port placement. So input ports, output ports that we need to place. Third one, macro placement. So macro is the biggest cells in our physical design. So that is the main third step. Last will be the physical cell placement. And what are the control parameters of floor plan? One is aspect ratio, core utilization. So aspect ratio will define the size, or else we call as yeah, size of the or shape of the chip, we call that. So aspect ratio is nothing but about height by width or width by height. So it will be shown the height shape of the chip. And core utilization. Core utilization is nothing but about how much area we need to occupy for this placing the standard cells, macros, and some other logical cells, standard cells, and all. So how much area we need. So suppose that the 100% area is mean, if you give 0.8 means 80% of the area will be using for the only placing the standard cells, macros, and other cells. Remaining 20% is used for the routing, like APIs, shapes, rings. So for that purpose, we using a remaining 20% area. So these are the two main control parameters of floor plan. Yeah, now you can see. So these are the four steps: core core die boundary creation, IO port placement, macro placement, physical cell placement. Yeah. So creation of core boundary creation is nothing but this is the die boundary, whatever that I am showing now. So this is die boundary, and inside is there na small square. So this is a core boundary. This is a core boundary, and in this core area only we need to place all the standard cells, macros, and other cells. So this will be given with this command: initialize floor plan hyphen core offset. So offset is nothing but what, whatever that you can seeing here na. So between the core to die we have some space here. So this space we call as what? Offset, core offset. So this will be given for the adding some power rings purposes. So for that we need to, yeah. Okay. So for that purpose, we need to give the space between the two die to core area. So in this area only, we need to create a power rings, and input ports we need to place, output ports we need to place, and this is a side one we call side two, side three, side four. If it is in a square manner, so there are sides, total four sides will be there. Suppose if we go with some rectilinear shapes, like as based upon the aspect ratio, if it is less than one, then it will go the another shapes like rectilinear L shape or R shapes. So that time what happened, that sides will be goes more. Output full screen. Okay, we have only two. Yeah. So first, so this is the creation of boundary creation. Okay, core boundary creation. Second one is nothing but what? IO port placement. Before placing the port, first we need to separate the input port separately and output port separately. So that will be the first thing we need to do. So we can do this by using tool options, or you can do it by using command also. So there are three steps involved in the IO port placement. First one, create the ports, set the port, and place the port. During the create, we need to give the boundary, how much area need for the placement of inputs. Second one, set is nothing but what? So after placing one port, how much space we need to give between another for the another port, and what is the distance of that, and which side we need to give, so that everything will be given in the set command. Then last will be the place. So these are the main three steps in the port placement. Coming to the third stage, that is the macro placement. So macros may be memories, or we call as analog blocks. Proper placement of macros has a great impact on quality and the performance of the ASIC design. And macro placement can be manual or automatic, and manual macro placement is more efficient when there are a few macros to be placed. And manual macro placement is done based on the connectivity information of macros to IO pin pads and macro to macro. Automatic macro placement is more appropriate if the number of macros are large. So this is nothing but what, as I told, macros are nothing but a biggest cells in our projects. We also called as the memories or analog blocks, or also we call IPs. IPs in the physical design. And so yeah, so we can do this macro placement with the manual and automatic also. So if the macros are countable, either it is enough like a 4, 5, 6 or something, so then we can do go with the manual placement of macro placement. Either if it is the more number of macros are there, suppose uh, more than like 100, more than 200 macros will be present in our project, means then that time what we need to do, go for the auto placement. So these are the two possibility will be there. So what type of macros we have? First one is hard macro, soft macro. Hard macro is the circuit was totally fixed. We can't see the functionality information about the macro. Only we can see timing information. So that is hard macro. Coming to soft, circuit is not fixed. Here we can see functionality and which type of gate are used in inside of that the macro, and also we can see the timing. Here we can see both timing and functionality, but the hard macros we can't see the functionality, but only we can see the timing information. So these are the main two difference between the hard macro and soft macro. Yeah, so coming to the during the macro placement, we need to follow some guidelines here. Placing of macros is very very important because after that this one at the later stage we getting a optimized routing area, right? So that is the purpose placement of macros will be take very carefully here. So first guideline is placing of macros are the based on the fly lane analysis, or else we call as communication lines. So how many times that one macro is communicating with another macro. Suppose two macros communicating with a more number of times means then that two macros will be placed in a one particular area. So that is the first guideline. And placing the macro around the boundary of the core, or else we call edge of the core. Suppose if the macro will be there means first we need to place the edge of the core area and boundary. We can't add it in the center of the macro. Why? Because macros are the power hungries, so they need more power. So if we place near to that core boundary means then, as I told, in between the core to die we creating some power rings, right? So from that rings whatever the stripes will be coming top metals from that, directly that macro will be getting a power. So for that is the purpose we need to place the macros at the boundary of the core. And macros are communicating with the pins and ports of the core. Place them near to the core boundary. As I told, same communication lines or how many times it will be communicating with another macro. And place the macros of same hierarchy together. Suppose two macros having the same number of pins, same height, same width, and the same color also. Then that two micro will be placed in the one particular side, and keep the sufficient channel between the two macros. So as I told, two if the two macros are placed with the one side means both are communicating. So communicating means they will communicating with the through the what? Pins. So if the pins are there means we need to connect it with the metal layers. So connecting between the two pins we need some space, right? So for that we given a space between the two macros. So that space we call as what? Channel width we call. So channel width equal to number of pins into pitch divided by number of layers which we are using in our project, either high horizontal or vertical. So that only I take one example, like total number of pins will be 50 plus 50. Two macros are there. One macro having 50, another macro having 50, and which metal layer pitch we are using 0.6 and divided by total. If we suppose we are having 12 metals means then using a zero point 0.6 divided by 6 is a horizontal or vertical, and we're getting one value. So this is the space we need to give between the two macros. Okay. And yeah, so coming to the halo, so this is a macro, whatever I'm showing here. So this is a macro. Around the macro only we added one more square, right? So this we call as what? Halo, or else we call as it is what? Keep out margin. So why we need to add and what it was actually, we will go with this one. So this is the region around the fixed macros so that no other macros and standard cells can be placed near the macros boundary. As I told, it is a macro and each macro having some pins. So that pins will be communicating with another pins. So that is the purpose we adding protection purpose around the macro one keep out margin. So if we add one keep out margin, then no other cells will be placed near to this macro pins. So if the macro pins are in this right side, then no other extra cells will be placed in the pin side. So that is the purpose we will adding around the macro halos, or else we call as keep out margin. So that is the main thing we need to add. We have different type of keep out margin. First one is hard keyboard margin, or else called a hard halo. So this is a type hard which we are using around the macro. Why we adding hard means the latest is if the hard macro or a hard halo will be there means it won't allow any standard cells or buffers or anything. It will particularly it will be block this area. So that is the purpose we adding a hard halo or hard keyboard margin. So blockages we call keyboard margins or blockages. Blockages are the specific locations where the placing of cells is blocked. And one more thing, halos and blockages both are same, but halos can't move. Blockages will be sometimes it will be movable. So that is the only difference. These blockages will be used for during the cell density, pin density. We getting some congestions during the placement stage, later stage. So there we can use this one. But now we are adding some keyboard margins in the macro purposes. So blockages are the specific location where the placing of cells is blocked, and blockages will not guide the tool, but it allows the this one allows but it allows not to place the standard cells, buffers and inverters at a same particular area. So different blockages will be present, like soft blockages, hard blockages, and partial blockages. These are the blockages type. So each blockages have some criteria. So suppose if you go with the hard macro, it won't allow anything, either it will be inverters or buffers or standard cells, it won't allow anything. Okay, same thing if you go with the soft macro, only allow the buffers, only allow the buffers can be added in the area. It won't allow any standard cells and this one inverters, only add the buffers. So this is a command which we're giving for the adding a type soft. And here we can go, this is the command which we're giving for the type hard, but the keyboard margin and halos will be same only, and blockages also work as the same only. Some particular area it will be blocked. So that is the purpose only we using a blockages. Yeah, this one done, right? Soft blockages, hard blockages. Yeah. So hard blockages means no standard cells or macros and buffers inverters can be placed within the specified area during the course placement optimization and legalization, and used to avoid the routing congestions in the routing congestion at the macro corners and control power rails generation at the macros. So yeah, that only the main thing. Hard macros won't allow anything. It will be totally particularly blocked some area. And soft will be allow only buffers. Apart from the buffers, it won't allow anything. These are the main two different hard macro and this one. Sorry, hard blockage and soft blockage. Coming to partial blockages, partial blockages will be uh, allows in the percentage manner. Suppose if one partial blockage is added means 100% of cells will be present. If you add partial blockage, then 40% will be distributed out that block from that square. 60% will be present inside that. So this is how partial blockages will works. And these type of partial blockages we are using for the cells in a particular area. So that is the so that area getting some congestion means cells are more, but that area getting some congestion. Why it will getting congestion means cells are more, but the tracks are less. So but each cell is having a size. So some of the cells won't getting that. In some of the cells we are using for the cell particular area. So that is the purpose only we are using for the partial blockages. So from that place to another place. So from that place to another place. So that will be distributed another place. So 100% means 40% will be distributed from that area to yeah. So in the last stage in floor plan is physical cells placement. So these are the cells not present in the design netlist. Why it is not present in netlist file? Anybody know? Anybody know this netlist file? Why? Because netlist only having a sorry. Yeah, okay, yeah. So the thing is, the netlist will contain physical cells placement. So suppose if you go with the it will require for that cell start the annual continuity also. So from one block to another block, it will start the annual continuity. For that purpose, we need to add the filler cells, and we need to fill the empty cells with the filler cells. So for the density errors also, for the main thing is, and yeah. So this is the floor plan of our projects. So you can see whatever that these blue colors are there now. So these are the macros. So these are the macros, and whatever you are seeing here now, red colors in the right and left. So these are the IO ports. As I told, these are the input ports, output ports. First input ports we separated, then we'll place it on side one, and output ports separated and place it in another side. That is a side three, and you can see the space between this square. There are two lines are there. So one is core area, one is die area. Between that, we need place the IO ports. I will open that our tool now. I will show that how that floor plan it was. One second. Yeah, is my screen visible? Anyone please confirm me? Is my screen visible?
Yes, sir.
Yeah. Okay, ma. So I'll open one more project. So it won't have any ports, right? So this is a tool which we are using for the physical design. So the tool name is Synopsys ICC2. We have different tools like in Cadence we have Innovas, and same in Synopsys we have ICC2 Fusion compiler, and some ICC and some DC compilers also we have. So these are the tools which we are using, and for CTS and routing we are using some Prime tools. Coming to Cadence, we have this one, Innovas and Genus, Temp something is there. So these are the tools we are using in our industries. So using these tools only, we need to do the physical design. Yeah. So you can see here. So this is the shape of another one, not it is in a square manner. So we use it in a U shape. So this is we call as rectilinear shape. So it will be given by using as some aspect ratios, core utilization. So this is a different core boundary equation. Whatever you can see here, that these are the die and core boundaries. One is core, inside one will be there now. This is a core boundary. Is it visible now? So this is a core boundary and this is a die boundary. In between we have some space, right? This space we call as offset values, offset value. So you can see here I place the input ports at one particular side. So this is side one. In between this area only we place the all the ports. These are the input port one, port two, port three. So you can see the different the spacing also. So one port to another port we given some space. So this is how port placements, even in the output side also. You can see here, these are the output ports. Okay. And whatever you are seeing, this biggest cells, these are the blue color. So these are the macros. So you can see this one and this one, whatever I highlighted now, this one and this one. So these are one hierarchy, and you can see the macros are placed at the edge of the core area only. You can see here this one also, these also, and we place the edge of the core only. Why? Because of they need power more. We call as power hungry area. If you switch on the pins here, all the pin of the macros will be face inside only. You can see the red color pins of the macros will be face inside only. You can see the red color pins of the macros guideline. And yeah, one more I'll show you. And if you click on this macro and if you go net connection, it will show how many times it will be connecting with some cells. It will be communicating with that cells with the 2 times or 3 times. So that is the purpose. We will place this one here. Same if you click on anyone, it will show how many times it will be communicating with another this one. So this is called as communication guidelines or fly line analysis. Using this only, we need to do the floor plan. And whatever that inside you are seeing now, these are these are the tab cells we call as well tab cells. Why we are adding these well tab cells means for the prevention of, I told right, prevention of what, latch up issue. So in between the one tap to one tap we given some space right here to here. So this is a space, the one VDD will goes and one VSS will goes. In between VDD and VSS one tap cell will be preventing the two nets. So you, for this we can easily prevent the latch up issue. There is a chance of low resistive path create between a VDD and VSS. So for that creation path it will avoid the this one, this tap cell will avoid the that path. So this is how we need to do. and you can see that boundary cells also. At the boundary side, we placing some boundary cells. So you can see this one. So these are the boundary cells. So they already wrote also. You can see the naming also is there. Boundary, right boundary, and even the tab cells also they tab. So these are the tab cells. These are the boundary cells. Boundary cells will be placed only at edge of the core boundary, right and left. It will be depends upon project. So if they given boundary cells top bottom also, we need to place it. But in our project, we have only right and left. So that is purpose I placed. And what else thing is there? Yeah. So as I need to show that this one also, right. Keyboard margins around the macro. I need to show that. So if you switch on the keyboard margin, you can see here. So this is the keyboard margin of around the macro. If we switch it on, switch it off, so that blinking is there now. So this is a keyboard margin around the macro for the protection of macro. You can see now. So around the macro, the keyboard margin is there for the protection of cells. In that area, you can see no standard cells or no physical cells will be placed in this area. This will be totally blocked because of the hard keyboard margin. So this is how the macro placements can be done, and physical cells can be done, port placements can be done, and core and die boundary creation will be done. So yeah, up to here the today's physical design is done. Tomorrow we'll go with the power plant placement, CTS and routing. I will show how it will be looks, and we'll conclude it in tomorrow onwards. Sir, are you there, sir? There, sir.
Yeah. Okay, Rohan. We'll continue tomorrow. Yeah.
Shall we continue tomorrow?
Yeah. We'll continue tomorrow. Yeah.
Thank you, guys. Thank you so much.